Hey folks, I'm Domotro. Welcome to my combo classroom again, where today I want to tell you some cool facts about numbers in the 30s and how some numbers in the 30s, like 30, 31, 32, 36, and some of those, are even cooler than numbers in the 20s. I mean, numbers in the 20s have 24 is a factorial, 28's a perfect number, 25's a square, and 27's a cube, but I would argue that the numbers in the 30s might be even cooler. Now, I am thinking about that to a degree because I am turning 30 this month. I'm not going to say the exact date, but it was within a week before or after this video. I am 30. And a lot of humans judge that number based on being a landmark. You're in your 30s now. Your tens place of your number now says 3. Based on it having a 0 at the end and the new tens place digit. But that's dependent on our base 10 system, and there are many other cool traits about 30, as well as some of the numbers following it, that aren't dependent on base 10, that are base independent traits, some of which we can visualize geometrically with dice. But since it is near-ish to my 30th birthday, I did want to set up real quick a few extra birthday presents I got. My family did get me some stopped clocks again. Last year and this year, they deduced that the best birthday present for me would be to help me with my clock quest. All of these stop clocks where I've promised hundreds. And a lot of people have thought maybe I'm falling behind because we break clocks as often as we get them. You think. But we've gotten some new clocks. Here's a clock and a variety of small ones. So here are some new clocks that we've gotten. All these little clocks of different sorts. And that is going to be added to our collection as all of our, well, not all of ours, because we actually got even more clocks. Stop clocks to continue the clock quest. Now, yeah, so luckily we got all of those clocks and these other clocks. Oh yeah, we got a lot of clocks. Okay, now to finally move on to our main topic, except that we would move on to our main topic except one thing. That one thing is that there's more clocks. So, okay. These will help us demonstrate a lot of modular arithmetic patterns in the future. Now, I'll just make a stack of our clocks for now. We'll hang them up on the trees and the fence later. Now, speaking of these numbers, 30. The age that I'm turning now, that I would argue its coolest traits are buried by the fact that it ends in a 0 in the base 10 system. Some of the coolest traits of 30 can actually be visualized with dice. And we're going to not use these dice in terms of what numbers showing. Ideally, I would put all ones on top. Maybe I'll flip them to ones when convenient. But the point is, each of these is going to stand for a cube. 1 unit cubed. Now, how could we use 1 cubic unit to demonstrate traits about numbers like 30 and a few numbers in the 30s I want to talk about? Well, let's get 30 dice. And remember that each of these is just going to be considered 1 unit regardless of what number is showing on top. Well, there's 10, 3, 4, 7, 10, and here is another 10. Don't worry, we got enough dice. We have more than enough dice. We have a whole dice carpet growing down here, but we don't even need to unearth any of those because here are 30 dice. Now, with these 30 dice, we can note some traits about 30 that can be expressed geometrically. Like, there are many rectangles I can form out of it. It's a very divisible number. It's not quite on the highly composites list because 24 is so divisible that 30 only ties it in how many factors it has. And to be on the highly composites list, you have to set a record in that trait. So 24 kind of was so good that 30 does not get on the highly composites list, but it's really cool in some other ways. Here I have it in a 3x10, but what if I put it as a 5x6? These are two consecutive numbers, 5 and 6, multiplied together that leave 30 dice with no remainder. And that is a depiction of it being what's called a pronic number, or sometimes called an oblong number, a type of figurate number, which is a shape that you calculate the area and can look at sequences. Like the pronic numbers would be 1 times 2, 2 times 3, 3 times 4, and so on, up to, including at one point, this 5 times 6. 30 can be expressed as a pronic number. Now, pronic numbers are pretty cool because we also can turn them into the sum of two triangular numbers. Every pronic number is the sum of two sums of natural numbers. A triangular number can already be seen as a sum where you put... Oh, squirrel. Ooh, I love when the squirrels come. Yeah. Okay. So, triangular numbers can be seen as adding all of the whole numbers from 1 up through something, but we can visualize them with dice. Arguably, they're easier to visualize with circles for triangular numbers, and when we look in a minute at a number that is a triangular pyramidal number or a tetrahedral number, those are essentially easier to depict with circular or spherical things, but we got square things for now, so that's what we're working with. They're easier for some of the other traits as well. Now here, look. This triangular number is 15, the sum of the first 5 numbers. We're not caring about what's on top, we're caring about how many units there are. That one's also 15 as a triangular number. They add up to 30, and it's actually true that every pronic number you can make as a double of a triangular number copied twice in a way. So we could even make it into an almost like rhombus-like shape. I could have flipped this and made it sort of symmetrical that way. So that's even a strange depiction of the number 30, is this rhombus shape. But that's not all we can do with 30. The thing is, one of the most crucial traits about 30 is that it is not just a pronic number, but a similar sounding term, a sphenic number. So yeah, pronic, which I'm going to call them oblong numbers probably in my episode, because those are, they're oblongish shapes. The pronics are a number multiplied by the number right next to it, an almost square rectangle of area. Here, the sphenic numbers are numbers whose prime factors are 3 distinct primes, each just once. So, for example, if I have whichever number is 7 times 11 times 23, that is a sphenic number because its only prime factors are 3 primes each once. Now, we could even turn those into a geometric representation because with these dice, we were looking at sort of the flat area on top when we were calculating the triangularness. However, if we look at the 3D structure, because we do have the capability as humans to look into the 3rd dimension, further powers get harder. It's a problem that, it's harder to do math with the 5th dimension, and it shouldn't necessarily be, but there are human limits to visualize stuff. But here, in the 3rd dimension, we could say, what shapes can we make into a prism with no remainder, where each side of the prism is a prime number? And those are sphenic numbers. And it turns out we can do 30 that way, because it's 2 times 3 times 5. In fact, one of the most important traits about 30 that I went into in a little more detail in the last stream on this channel. You can see those after the fact on the live tab. I keep the videos of them. Here is a 2 by 3 by 5. One of the more important traits is that those are primes and the first 3 primes. So 30 is what they call a primorial, kind of like a factorial multiplies all of the whole numbers up through something. A primorial just multiplies all the primes through something. And this is either 5 primorial or also 6 primorial, all of the primes multiplied up through those. 2 times 3 times 5. And we can see it visually here. It's like a 2 by 3 by 5 prism with no remainder. Now, what about 31? Well, 31 seems to throw this completely off, because one of the first traits we'll note about it is that not only can it not form any prism, if a number could form a prism, that would imply it has at least 3 distinct factors that can multiply together into it. But it also can't even form a rectangle apart from a 1 by 31. There's no way to turn 31 into another rectangle. And that is a way to depict prime numbers. Not going to make the really long snake of 31 in a row, but the only rectangle I could make out of these dice is a 1 by 31. Or rotated, we could call that a 31 by 1. Those are the only factors of it, making it a prime. However, that's not where the story ends with 31. We can go further. 31 has a really cool trait that we're actually going to observe through 32. 32 is a power of 2. 32 we can get by doubling something a bunch of times. Here's a quantity, doubled. Now we're going to double that quantity. Now we're going to double that quantity. Remember, numbers on top don't matter, just about how many units. Double that quantity. Now, when we double that quantity again, we get 32. It's a power of 2. In binary, it would look like 1 and then a bunch of zeros. Only a single 1 in the mix in the representation on the spot that, goes along with 2 to the 5th power. However, we can do something really cool with numbers that are 1 less than a power of 2, like 31. We can make them by sums of all the previous powers of 2. 1 plus 2. So we take that, we double it but as a copy, double that but as a copy, double that but as a copy, double that but as a copy, and now we have 31 dice. I had set aside the 32nd. So 31 can be expressed as the sum of the first 5 powers of 2. So then we could write that in binary as just ones. 1, 1, 1, 1, 1 in each of the spots representing powers of 2. And numbers that can do that, that are 1 less than a power of 2, that are also prime, like we showed, it can't fully make a rectangle out of all this. That's not 1 by 31. This one's the 32nd. Are called Mersenne primes and are super important and include the largest primes known to humanity. So 31 is in the family of the biggest primes currently discovered. Now 32 we said was a power of 2, and 36 we can do other things with. Now we can even find ways to visualize the other dimension. I meant 33. We're going to skim past a bit because 33, while it looks cool in our base 10 system, it's not one of the coolest in the 30s. Looks super threeven, you'd think I'd like it, but it's 3 times 11. It's not one of the coolest. I do actually want to jump to 35, because 35 has the trait of bringing the third dimension into it via the triangular numbers. Now here, let's make the first few triangular numbers. So I have 1. 1 plus 2 is 3. Adding through 3 is 6. Adding through 4 is going to give me 10. And these remainders will add to the 5th triangular number. I got 35 of them because I knew 35 can be expressed as the sum of the first 5 triangular numbers. 1 plus 2 plus 1 plus 2 plus 3 plus 3 plus 1 plus 2 plus 3 plus 4 plus the same thing up through 5. Now, we can even stack these. Like I said, these are easier to visualize with spheres. If I had spheres, these would line on top of there really well and snugly. They would fit right into those gaps. So would these. They would form a nice little pyramid. This is known as a tetrahedral number, sometimes a square pyramidal number it's called. No. Triangular pyramidal number. Because we're using triangular. Square pyramidal numbers include other things. Square pyramidal numbers would include 30. If I remove a few of these, I'll make 30 into a square pyramid. This is a triangular pyramidal number, but I like the term tetrahedral. Now, that's 35 expressed as the sum of the first 5 triangular numbers. Similarly, like I said, we can do 30 dice and express it as the sum of the first 4 square numbers. If I add spheres, this would also fit a bit more snugly. These 3-dimensional ones, if you imagined with marbles or cue balls, would fit right in the gaps on top right here. Feels pretty windy out here today. Pardon if there's a lot of wind in the audio, folks. Now, right there, I have 1 plus 4 plus 9 plus 16. And that gives me 30. So there's 30 as a square pyramidal number. Now, I said that we're going to go on some in the lower 30s. And that's because 33 and 34 are alright, but they're just composite numbers with other cool traits. But the next one that I thought was most important to visualize geometrically is 36. And now I have 36 dice here. 36 is so cool because not only are there so many rectangles, I could make this a 1 by 36, or any of these could be flipped like 36 by 1, a 2 by 18, a 3 by 12, a 4 by 9, and even a 6 by 6, making it what we can call a square number visualized geometrically. You know, like a square number are the amounts of dice that can make a perfect square. Now, not only is 36 a square number, but I could make it into a triangular number. It's also the 8th triangular number, or the sum of the first 8 numbers. Now, it has other very neat traits, like how 6 is the side length of this square that has 36 dice, and 6 is a triangular number. And I mentioned that we could turn 36 into a triangular number as well. Now, I read that apparently 36 is the only number that, apart from 1, that has its square, and apart from 0, I guess, 36 is the only number apart from those that its square root is triangular, and it is triangular. I could not find the source of that online. I read that it was in this old textbook that costs a ton of money, so I'm going to go to a library sometime to confirm that fact. It also will give us fun facts about 6, because we could also say, once I confirm that fact by finding that book in a library somewhere, we will then know that 6 is the only number that is triangular, or could be the side length of a square of a number that also could be triangular. 36 is also the first 2 primes then multiplied by that. So here's a 2 by 3. Well, that's a 2 by 3 by 2. There's a 2 by 3, 6. And if I give myself that amount of them, I get 36. I can make 6, which was the amount of those. And each of these are based on what we could call either a primorial or a factorial. Primorial is the product of the primes up through something, and these are that. 2 times 3 are the first 2 primes. We could also say it's the first or the third factorial. And it is 1 times 2 times 3 if we analyze the upper dimension. In fact, I could make that into the next one. In fact, one of my favorite traits about the number 6 that I love is that it is the third triangular number, which we can visualize that way, and that it is the third factorial as well as the primorial up through 3, which is 1, if we look at the height here, times 2 times 3. So this equaling that, equaling 6, is a pretty core combo class trait that will show up many times in the future.